Assalamu alaikum. My name is Mohammed Bilal, and today I'm here to give you a descriptive presentation on the line following robot that we have built as a semester project for the microcontroller and embedded systems course. This is not a simple line following robot. This is a line following robot that has multiple other features, such as the obstacle avoidance and color sensing capabilities. Now, this project is a 1 month long project that was started from the mid of November, and it went on till the December 20th. So let's start off with the first idea of the project. The first thing while building this project for us was to calculate the feasibility of this project, that whether this project was possible or not, because we were familiar with the line following robot before starting on this project. So that was a plus point for us because we already had familiarity with the line following robot. All we had to do was implement the obstacle avoidance part along with the color sensing part and the encoder motors part while integrating it with a printed circuit board rather than a Arduino connected with jumper wires and just naked wires. So the team roles were as such that the first phase was the project initiation, where we had to lay out the outlines and the objectives of what we were going to achieve with this robot, which is named RAHBAR robot. So the first thing was obviously the line following capability. The next was the obstacle avoidance. The third was the color sensing portion. That when it senses a object of a specific color, it should either stop or it should either rotate back and go back to its original position by using the encoders and that the position that the encoder has given to it. So the first step was the implementation of the line following robot. So the main things for the line following robot was the sort of which sort of IR sensor we were going to use, which motors we were going to use, what type of tires we were going to use, and what type of motor driver would be best suitable for the motors that we have decided to use. And obviously, we had to make sure that we're using as minimum of the wiring that is possible. So the PCB came in two part in this part. So the third step was the PCB design and fabrication, where we designed the PCB on Proteus with the with the help of our fellow mates, and then was the fabrication, where we etched the PCB ourselves. We printed the PCB schematic, and then we etched the PCB. Then we bought the sensors, including the obstacle avoidance sensor, the ultrasonic sensor, the color sensing sensors. Then we bought the encoder modules that we used in this specific project. We have used the optical encoders, and the power management was done in the sense of using 3.6 volt cells that were, I think, 2 amperes. Yes, around 2 amperes. Yes. So a total of 12 volt was supplied to the robot. And we also have used the ESP32 cam version to provide it wireless communication, because we have used the encoders and the SD card part of the project on the ESP32 cam separately, and the communication is done between the Arduino Uno. The Arduino Uno has the line following robot in it, the major aspects of the line following robot and the obstacle avoidance. So the communication between the encoder and the motors is done through the ESP32 cam. So, and the last is obviously the final testing and demonstration process. So we were comprising of 3 students, including me, Muhammad Bilal, Anas, and Afaq. So we divided the project into like 3 main categories. One of them was the objective or the task of the main team lead. That was me. It was the project management part, where I was overlooking all the major aspects of the project, including the hardware design, the software design, the component ordering, from everything from A to Z, essentially overlooking the whole the project procedure. The second main aspect that we had divided was the hardware portion, the hardware engineering portion, which was given to Afaq, where he developed the chassis of the robot. He did the soldering portions and the main integration of the sensors and stuff like that. We all did put our hands into all of these specific tasks, but this was the major task that we had given to a certain team member. And the last was the software engineering part, where we had to code in the Arduino IDE, which was done by Anas on the most hand, where he did the research for how to use the color sensor, how to use the ultrasonic sensor, how should we detect the red color with the color sensor, black color with the color sensor. He did that portion, and then we all obviously implemented it together in the final project code. So this is a Gantt chart representation of the timeline of the project, where we have given the major 12 aspects of our project that we had divided into. As you can see, it has started around like 19 to 20th November, and then it finished around 24 December. So the first major aspect was obviously the literature review and the component selection for the LFR. We did some prior research on the internet, including looking onto some research papers. We also looked at some uh, products that had been already implemented in the market, and alongside some patents as well, which we have mentioned in the report further down. And we also obviously looked at the component selection portion, where we saw which components are available uh, easily rather to us, and in available near to us in our domain. And then the second part was ordering those components, which included the motors and the sensors and all that stuff. The third aspect was the PCB software design, where we uh, designed the schematic alongside with the PCB layout on the Proteus software. Then the next part was obviously getting that PCB schematic, the PCB layout, to print it on the paper, and then we etched our PCB with the specific PCB design that we had made. And then the next part was, after etching, was soldering the components that we had ordered. That included different sort of capacitors as well, some sort of capacitors for the battery to make the battery better, the signal from the battery. And then the next part was the assembly of the chassis, where we implemented the PCB, integrated the PCB, the ultrasonic sensor, the color sensor, the QTR sensor, that is the IR sensor that we have used, with the body of the robot, including the motors and stuff. And then the eighth part was coding. The major aspect, which took us the most time to perfect and to research on, was the coding for the RAHBAR. That how could we implement PID control for our line following robot rather than just using basic if else, and how should we get the ultrasonic sensor to work, that when it should detect a object from a certain distance, it should stop, and then it should initiate the color sensing procedure, where it checks which color is in front of the robot. If it's red, it should stop, or it should go back, or if it's black, and vice versa, depending on whatever color we chose. And then we did some modifications to the code and assembly after we had written the initial code, understanding that what aspects would needed changing, such as the placement of the sensor, placement of the battery to adjust the center of gravity of the robot so it senses the line better and moves forward better. And then we had the final testing phase, where we, after the modifications, implemented all the aspects that we had completed, and then we had our fully working robot. Then the I'll get on to the introduction. I'm done with the introduction. These are the research papers that we had interviewed, as I mentioned above. This was done by the help of Google Scholars. We looked on to some of these research papers, along with these commercial products, this XYZ line tracker services, the SwiftNav navigator, the RoboTrace. These are all available on the internet, and we can look onto them and get inspiration from them. We also looked onto the Zoomer robot that is available in our robotics lab, and also took some inspiration for that. These are some of the patents. Now, this is the main operational specification of the project, where the main three things, the first major three things, were the QTR sensor, which is the IR sensor array that we are using. It has a total of 8 sensors, but we were only using 4 channels because of the pin restriction on the Arduino Uno. We could have used the Mega, but it wasn't available for us. We already had a Uno laying around, so rather than spending more on a Mega, we just used the Uno and went on with a 4 channel of the IR sensor. This IR sensor gives detects the line whether it's black or white, depending on which tape or which track we are using. It gives the reading to the Arduino, and then depending on that reading, we adjust the motor speed, the motor control. The next major aspect was the ultrasonic sensor, which detects obstacle in front of it and when to stop and when to move and when to rotate. Third was the color sensing portion, where we detected the sensors. And then there was the motor driver, which is used for controlling the motors depending on the reading that has been given to it by the color sensor and the ultrasonic sensor and the IR sensor combined. So we control the direction of the motors and the speed of motors using the L298N motor driver, because it is the most feasible and most easy to use motor driver for beginner level. We also tried to use the L293D motor driver, but it just short circuited on us twice, so we just shifted to the L298. The L293D has a better library for controlling the motors. It's quite simple, but I don't think it's very practical for us. It wasn't for us because it just short circuited twice. And the L298 was a hit. It worked fine. Then the major microcontroller was the Arduino Uno, which had the line following, obstacle avoidance, and color shifting portion. The ESP32 cam already had a built-in sensor. That's why a built-in SD card module. That's why we bought the cam version instead of the ESP32 basic one. So we didn't have to buy another SD card module. So the SD card module and the encoder part of the motor was implemented in the ESP32 cam. As I was mentioning, the encoder module, which were the optical sensors. We also used a buck converter in our robot to provide the motors and the motor driver with a stable 12 volt, so that the line following sensing portion is efficient. Then the PCB fabrication, the robot chassis, and obviously the Wi-Fi module was already present in the ESP32 cam, so we didn't have to buy another one. And for batteries, we had used 3.6 volt cells. So the basic operation was, obviously, the first part was the sensor array reading, where the QTR sensor reads the data depending on the amount of light it absorbs or it's reflected from the surface, particularly in the presence or the absence of a line. Then was the line following algorithm. Now we decided to use the PID algorithm for the line following aspect rather than the if and else, because the PID PID algorithm is way more efficient than just using basic if and else for more complex arenas. So the motor control commands were given to the L298, as I mentioned, where we set certain pins of the L298 to high and certain to low, depending on what direction we want the motor to be going in, a specific motor. And then there was the proportional control, where we uh, set some base speed limits for the motors so that it may not go off track when detecting right cuts or left cuts. So, and then the last process was the continuous iteration, where we implemented a wide loop, a while loop, essentially a super loop, where the robot continuously detects the line and waits for further instructions. So the main component list was as given, where we had the Uno, the chassis, the ESP32, two motors. We used N20 motors because they are high RPM motors and they're pretty good, better than the TT motors, because TT motor tires that they don't have very good grip. The N20 tires, on the other hand, are rubber tires and they are very grippy, and they're very fast as well because they're high RPM motors, and they're low torque, so there is a setback. We had the SD card module that was built in. We had some resistors and capacitors for the battery, the QTR sensor, the on and off button. We also had implemented a interrupt button, a emergency stop button that was connected to the interrupt pin of the Arduino. Whenever you pressed it, the robot stopped. Then the major these are the major components of our project. So as I've mentioned the major aspects, I'll be moving forward to the block diagram. Here is the following block diagram that we have implemented. This has the QTR array in it, the ultrasonic, the color sensor integrated with the Arduino Uno, the L298 connected to the motors and the battery, and the buck converter coming from the battery. We also had voltage and amplifier sensors connected to the battery so that it gives the battery time to the user, that how much battery is left and whether you need to charge it or not, just like your phone's battery health, which gives you the percentage. We were giving the voltage. And then there was the ESP32 cam connected to the encoders and the built-in SD card module. So I'll be moving forward. I have already discussed this portion of the algorithm and all that stuff. Now this is a picture or free body diagram of the robot, where we have placed the battery at the center of the robot, so we have the best of the center of gravity for the robot to follow. This is an image where the ultrasonic and the color sensor are placed on the front, where the IR sensor is on the bottom, connected to the PCB. So the mechanical design, we used a pre-built chassis. For initially we had built a chassis using a fiber board, but it wasn't quite good as the pre-built chassis, so we just went for the pre-built chassis. The main aspect is the PCB. Our PCB is quite big, so it does act as a portion of the chassis. So all our major components are not connected to the board, but rather they're connected to the PCB itself, including the color sensor and the ultrasonic and the color sensor. The material selection, I've already discussed that. Now let's look at some of the major components that we've used. The ultrasonic sensor. Here is the ultrasonic sensor. It has four major pins: the VCC pin, the ground pin, the trigger, and the echo pin. Now the trigger pin function as the input pin, and it should be maintained at a high state for 10 microseconds to initiate the measurement process. This is the data that we have got from its data sheet. The echo pin is the output pin that it needs to be it's supposed to be high for the time it takes the ultrasonic wave to go from the input and then reflect back from the output and then come back. So this is the major pin out for the ultrasonic sensor. We explicitly use the HCSRO4 pin out. Then here's the Arduino Uno, the age-old Arduino Uno. As we know, it has analog pins, digital pins, RxTX, and the TTL adapter, and obviously the Atmega 328 microcontroller. This is the data sheet that we used for our references for the 328P, which we have already worked on. Then there was the L298 motor driver. This is the L298 motor driver, which has two motor outputs, two on either side. Then it had four interrupt pins and two enable pins, which are helpful for the coding aspect. And that the main also part of using the L298 was that the Arduino Uno does not support 12 volt directly. It only supports 5 volt for its operation. So we had a 12 volt battery for the motor, so all we did was connect the battery to the buck converter for the stability of the battery. Then we connected the 12 volt to the motor driver, and then from the motor driver we took out the 5 volt output and then provided it to the VIN of the Arduino Uno. Now here is the IR sensor that we have used. This is the 8-channel array IR sensor. It is the QTRA specifically. Of these 8 sensors, we use 4. We skipped one sensor. We use 4 sensors alternatively, like the first one, the third one, the fifth one, and the 7th one, so we can get the most of the sensor width out of it. And this is the color sensor. The one that we've used is the TCS3200. It has 4 S pins, the frequency pins essentially, and then there's an output pin, and then there's the output enable pin that we have used, and it also is operating on 5 volts in our circuit. It has an operation voltage of 2.7 to 5.5 volts. Now, this was the built-in SD card module in the ESP32 cam, which had the built-in module alongside the Wi-Fi module. So that was a good thing. It's similar to the Arduino in terms of coding, and it has its GPIO pins and the respective voltage in and voltage out pin outs. This was the ammeter. that we've used the voltage and ammeter display. This has the voltage and current sensors built in and integrated alongside it. This showed the battery output of our battery. Now this is the N20 motors. These are the N20 motors, the main crux of our essentially the legs of our robots. So these have an operational voltage of around 6 to 12 volts, and we were giving it around 11.5 volts. And it has it's quite compact in size. It's small. It's a gear motor. As you can see, the gears are already shown openly, and it has it's a low RPM motor. Sorry, a high RPM motor. And these are the N20 tires, the small tires that we have used for our robot. That was quite grippy, so it provided us a good compact. Now here is the PCB design that we had made for the RAHBAR. This is a PCB design schema, PCB layout that the PCB was implemented on. Now I'll zoom into the next portion. Now this now comes in the software and the firmware design, where we coded the line following robot on the Arduino Uno IDE. Using the Arduino Uno, we used the 32P microcontroller. We used the Arduino because it was the most common one. It has 14 digital pins and 6 analog pins alongside PWM and PWM pins. So the first major aspect was to code the line following robot. I'll go to the, this is, before going to the code, here's the basic state machine or the state flow diagram for the line follower, where it reads the line, and depending if the line is centered, it goes forward, and if it's not, if the line is towards the right, it goes towards the left, and if the line is towards the left, it goes towards the right. And if the data, it can't read anything, it's getting garbage value or some sort, and it just stops rather than just going and continuously moving forward. Here's the basic flowchart of the above state diagram. Now I'll move forward towards the code. Yes, here is the code. This is the code that we have used. The first aspect was the initializations of these specific pins, that where we had connected the motors, the enable pins, the ultrasonic pins, and defining the pins for the color sensor. Now here I've also initialized the variables, for the PID, the last error, the KP, the KI, the KD values. The KP, KI, and KD values are the heart of the PID algorithm, either than the main PID equation, because these are the variables that we control for the robot to follow a straight line. The KP is used, the adjustment of KP is done so that the robot follows the line straight, how good it follows the line without swaying too much. And KD and KI are for turning, that how smoothly the robot takes left and right turns. So the adjustment of KI and KD makes the turning more smoother. So the base value of the motors, the speed, we set it to 100. So minimum of 100 is set for the base value. Then we have defined the variables for the color sensor, the red sensor, the green sensor, the blue sensors. Then we have used the QTR sensor array library. It has a built-in library, built-in functions to read lines, to get the data, to decide whether it's going to be black line or blue line, black or white line. So we did use that. And here I've initialized the class object QTR that was supposed to be. Here in the sensor count variable, I have said that there are four sensors that we are going to use. Then I have made an array that has a size of 4 that will store the values of those respective sensors separately. Then I've initialized the pin modes, whether I'm using the motors as output, input. Obviously, I'm using it as output. The enable pin as output. The ultrasonic has the trigger pin is the output. The echo pin is set as the input, and also done for the color sensor. Here I have mentioned that I'm using the QTR analog sensor. That's why we have mentioned here QTR dot set type analog. Then we have mentioned which specific pins on the Arduino we have connected the IR sensors on. That's why the QTR dot set sensor pin has the analog A2, A3, A4, and A5, and alongside the sensor count that has the values being stored in it. Then we begun the serial communication at 9600 baud rate. Then this is the QTR dot calibrate function is the function that runs when we have to calibrate the sensors so they may get the idea of the surroundings and the environment, which we run for around 10 seconds. We have initiated a for loop, and then we have a delay of 2 seconds before the robot starts moving. Then here's the main void loop function, which has the PID control function. This PID control function is defined further down, which has the main LFR code, the PID equations and stuff. Then here we have after now when this PID control function runs, the robot is essentially following the line. So the next step is detecting throughout the process that when does the ultrasonic sensor detect something in front of it, because that's the first part, the detection of the object before the color sensing. So this is the code for that, where we put the trigger pin as high, and then as we mentioned from the data sheet, we add a 10 microsecond delay. Then we write the trigger pin as low, and then we read from the echo pin, and then dependent, this is some mathematical formulas to calculate the distance, and we have set a certain uh, baseline distance that when it's this much, it should stop. If distance less than equal to stop, then it should stop, and then we have simply just stop the motors. Now this, if color is black, now this comes from the color sensing portion that is further defined downstairs. I'll show you. This is before that I'll show you the PID portion. This is it, where we're using the QTR dot read black lines because we've used a black arena. Now this is for debugging this for loop. This for loop shows us the values of the respective sensors and the line position. That means that specifically if the sensor is in the middle of the black line, it should give a base value of 2000, so we can use this for debugging. Now 1500, because the maximum value that we can go to is 3000. So this is the middle portion, the 1500 minus the position line. This is the error. Then this is the PID algorithm, that P is equal to error, I is equal to error plus the integral, and derivative is the last error minus error, and the last error is the current error. And now this is the equation for the PID, where we get the motor speed from this equation, where P into Kp plus I into Ki plus D into Kd is the equation. This gives us the motor speed. Now we add the motor speed into the base value for the first speed, and the second one we minus it. Now if this is our certain restrictions, that if the motor speed is greater than 150, we want the motor speed to stay at 130, because we don't want the motor going too fast, so it goes out of bounds. This is the restrictions. Then this is the movement portion, that the as mentioned by the speed that we had. This is the first one is for the robot going forward, second one is for backwards, the other one is for left, and the last one is for right. And here is the RGB portion, which is the color sensor portion. It reads the color sensor. And this is the rotate portion, which if it detects a red color, depending on the frequency, because the color sensor checks the frequency of the color, because red is giving you a certain frequency and black is giving you a certain frequency. If those frequencies match with the sensor, then the respective code gets played. So that was the basic idea of our code that we had used. I'd move on towards the schematic. Here, this was a schematic that we had used. This is the 32 ESP32, the ultrasonic, and all those wiring is present here in the report in detailed description. You can look through the report. Now this was the final testing phase of the project, where after we had conducted tests that the robot is moving good and everything is flowing smoothly. This is the final robot. Here, as you can see, we have attached the ammeter display, which shows the battery voltage, and this is the main robot that we had built. We had to use some wires at the end because the design wasn't perfect, but overall the robot was good enough and it used minimum wires. Now this was the overall project cost. That was around 10,000, because bear in mind, we did have the Arduino and the motors and the major aspects, the expensive things beforehand. So it did cost us around 10,000 overall if you look at it, because we had to buy everything. We had to buy ESP32, the Arduino, the motors, the batteries, the buck converters. The color sensor was quite expensive. It was around 1,500 rupees. And the battery was expensive. We had to buy wires, the ammeter displays, the sensors. So this was it. And the robot, this report was equally written by each of the members. This report is around, I think, 6,400 some words, and it was equally written by all of our members. We had distributed the tasks. Now, risk task, we did learn that we should analyze our surroundings and the targeted audience, and we should set on certain limits of the speed and certain emergency stop buttons in case of any sort of emergency. And this is the GitHub link. At the end, at this following link, you can find all the code files, also the schematics, and the Gantt chart and everything. It's mentioned here at the GitHub link. So that was it. This was our project of RAHBAR. Hope you liked it, and thank you very much. Goodbye.